and the boundaries between classical and quantum computers.
Thank you. I've heard a lot about this conference over the years. I've never been to one before. I'm grateful for the chance. I will try to respect the broad nature of the conference. My background is theoretical many-body physics, let's say, mostly focused on what actually happens with materials and atoms in the lab. However, there is some interesting progress where at least a few of the problems that we were working on anyway, quantum computers, in particular those at Google and IBM, actually have something to say. I don't know if I would claim it's sort of fully quantum advantage, but they've at least done things that would be quite difficult for my group to do with classical computation, let's say. So rather than start with the big picture, and I'm going to talk about a couple of years of work, so it involves a large number of people, and I'll try to mention them as I go along, but most of the theoretical work happened at Berkeley, people who are now scattered around the world, and I'll show some experimental data from a couple of groups, but the ones I actively worked with were at Oak Ridge and Duke. So just to kind of explain, why we're studying these particular quantum matter problems, a lot of progress in physics is made by understanding the fundamental particles and the fundamental forces, but sometimes we know that new particles and new forces emerge, and there's two particular styles of that have a long history in the physics of matter, and it turns out both of them appear in what you could view as the simplest non-trivial model of many qubits. I think about it in terms of spins, but if you just think spins are two-level systems for spin half, then it all makes sense. So one kind that gets a lot of attention is that sometimes we mix a bunch of electrons or nuclei, whatever, and we get some new kind of particle, a quasi-particle. Like in magnetic systems, you get something called a spin-on, which is like a piece of a spin wave. But sometimes you get a new kind of fluid. And rather than talk about too many different things, the main physics example I'm going to give is how a chain of qubits interacting locally in a certain way turns out to have a funny kind of fluid that is about an 80-year-old problem. Hans Bethe maybe took the first steps on this problem, but we only understood starting around 2019 what really goes on. And it turns out the reason why I'm talking about this funny fluid is that it's unusually suitable for quantum simulation, originally with atoms and just in the last few months with bona fide quantum computers with superconducting qubits. So I'll use that one problem, and the physics in hindsight shouldn't really have taken 80 years, and I won't get into that many technical details. I'll flash them up so that you know they exist, but I'll try to just give the general sense of why was this one problem accessible, why are most problems still hard, as I think you heard if you were at the last talk yesterday, and where are some roadblocks to going from a few special cases to a more general solution of hard quantum matter. So the case I'm going to talk about, physicists call the Heisenberg spin chain. You could view it as a chain of qubits with interactions that tend to form singlets, entangled pairs. And it turns out that things happened very rapidly in the last 5 years or so. There was a theoretical idea that could be confirmed to some degree with classical numerics. And then there were three kinds of experiment in quick succession. The three kinds were a traditional solid state experiment, which is bouncing neutrons off a crystal. There was an ultra cold atomic simulation of atoms in a lattice. And then there were more recently quantum computers in the sense that we usually mean quantum computer. I will talk in closing about, just to give you the sense that most problems we care about are still hard, an example of a current problem that we and other groups are working on, where experimentally there's clearly something interesting that, as far as I can tell, is inaccessible with classical computers and likely to remain so, but also currently inaccessible with quantum computers. So I think it's good to end with what are things that we'd like to understand. I mean, the good news is condensed matter still produces mysteries that are maybe, you could imagine them being solved in 10 or 20 years, but not exactly, we don't know how. And what I'll try to throw in, given the nature of this conference, is Google and IBM, I'm sad to admit, they don't care about these chains of spins for the reason I care about chains of spins. They care about these because once you let the couplings vary, so it's no longer a kind of translation invariant chain, then it becomes a useful problem from the point of view of theoretical computer science. So I'll talk about how different sorts of spin systems could be used to encode. I won't say much about the details, but just to remind you, I guess, of the complexity classes that emerge when you have interactions between different kinds of spins. All right, so spin, just to explain language, think of it as a two-level system. You can superpose the up and down states. That's a qubit. Maybe the first non-trivial thing happens when you've got two of these two-level systems. Because, for example, the antiferromagnetic interactions that are very common in solids, actually antiferromagnets are much more common than ferromagnets, but you needed the discovery of neutron scattering to really prove that antiferromagnets exist, and a lot of that work was done at Chalk River, I think, in Canada. Anyway, if you form a singlet, that's a nice entangled pair. We know that it's a pure state. It's the best description of two spins, but if we only looked at one spin, we couldn't describe it with a wave function or a pure state. We'd have to describe it with a density matrix. It has an entanglement entropy. The reason why quantum magnetism gets hard, even for very simple antiferromagnetic interactions, is that you can't make every bond in the singlet state. There's so-called frustration. And that motivated a lot of ideas that are still good ideas that it's difficult to realize in experiment, at least in actual materials. Maybe you could have a kind of magnet where instead of ordering in some simple way, you get fluctuating singlet bonds of this type, or resonating valence bond is what RVB stands for. And whether that is really a common thing in nature, we don't know. So first slide on maybe why this connects to spin models. If we could take even just classical Ising spins, you could write them in terms of quantum operators if you want, but they would all commute. This kind of Hamiltonian, if I'm allowed to choose the weights or the interactions, Wij, at least, you know, in sort of all-to-all models, this becomes very powerful. So a precise statement is, this is one of Karp's classic examples of, you know, a powerful problem that we believe is hard to solve, but easy to check, if you like. So it's NP complete in the sense that, you know, some people here know this much more than I do, but just for the physicists who might have crept in, if you could solve a model like this, the world would beat a path to your door, because in a sense, an enormous family of hard problems could be encoded in these terms. So even classical spins have a lot of power, where by classical, I mean like an Ising spin plus or minus one. If you have other kinds of spins, like happen more often in nature than Ising spins, then you get even more power. So to kind of rephrase Karp's result in quantum terms, finding the ground state energy of the classical Ising model on a large enough number of bits is an extremely powerful computer. And in quantum language, that's equivalent to finding the ground state of the Ising Hamiltonian just written in terms of quantum variables. So you might think, well, I could start with a hard ground state and kind of adiabatically evolve it, with an easy ground state, you know, all spins up or something, and evolve it into the ground state of this. That, you know, in practice doesn't always work very well for interesting ground states, that sort of adiabatic quantum computing approach. But it is true that more complicated ground states are more powerful. So I'll talk about a case where these weights are very simple, but it still took a long time to understand the physics. The good news is quantum computers are actually contributing to that understanding. All right, so now back to physics. If you look at spin in a solid, because I am going to talk about some experiments on solids in addition to experiments on quantum computers, the way many spin systems work is that one direction of spin is conserved. Let's say the total moment along the z-axis is conserved, and if you do that, the total number of, you could view that as related to a diffusion equation, and let me just kind of establish that relationship, because I'll talk about cases where spin is not diffusion. So in general, if I had a conserved number of particles, the most frequently occurring macroscopic description is a diffusion equation, and an important solution of that is the spreading Gaussian. So that spreading Gaussian has kind of an anisotropy between space and time, because it's got x squared over t, just to write it slightly larger. The way this translates to spin diffusion is that some spin direction, the total moment along that direction is conserved. I again frequently get Gaussian spreading, and a way to encode, you know, aside from the details of the Gaussian function, a way to encode what's going on is this dynamical critical exponent, z equal to 2. So if you had to pick one number to characterize what we call a dynamical universality class, it would be, what is the power law relationship between space and time? So for example, ballistic behavior, where particles have a velocity, x is linear in time, and z is equal to 1. So not everything in life is diffusive, and we know that when we add additional conserved quantities, hydrodynamics, the long time behavior of them, can get considerably more complicated. So this is maybe a simple model of a fluid. There are three equations, and you can add viscosity and things like that, but just to make the point, in a description of a typical fluid like water, there are three equations, and those correspond to the three conservation laws. We don't just have a conservation of particles. That's the first equation. We have conservation of momentum because the system is translation invariant, and we have conservation of energy. And one way to derive these is from the so-called Boltzmann equation, which maybe assumes, if we take the Boltzmann equation and we assume local equilibrium, we get hydrodynamics. So in general, this kind of theory is very useful to describe nature, from a drop of water up to like the Earth's climate. It's really about how local equilibrium, which is rapidly reached, evolves slowly into global equilibrium. Now, where this gets kind of interesting is that the simplest models you could write down of a chain of interacting particles turn out to have an infinite number of conservation laws. So if we want to do hydrodynamics, then in principle, we have to deal with an infinite number of Euler equations, which would be a hassle. So it turns out that there are tricks to get around that, and they're very physical, and I kind of want to sketch those tricks to you to explain why, from a physics point of view, we cared about this chain of qubit problem. But the basic story is that if I took either bosons moving in the continuum with delta function interaction, or the case I'm going to focus on, which is a bunch of interacting spins, and we often break out because of the symmetries of the problem and also how it relates to a fermionic representation through the so-called Jordan-Wigner transformation, the interactions in the x and y directions, which I'm going to assume are equal, and the z-directed interactions. In fact, a little bit of magic is, if I just had Jz, I'd have the Ising model. If I just had Jxx, I would have a model of free spinless fermions kind of wrapped up into spin operators, and it's easy to solve as a result. That's this Jordan-Wigner transformation. The Heisenberg point, the one that appears in many materials, turns out to be the most interesting. That's just when Jz is equal to Jxx. All right, so to try to convince you that I'm not lying when I say there are an infinite list of quantities, there's one infinite list that's been known for a while, at least back to the 70s. These are sort of the charges, and these are the currents. And when I write sigma with a bunch of superscripts, that means the product of Paulis on, say, 4 or 5 neighboring sites. So they all have compact support. They're localized on a certain number of adjacent sites. The magic is this old list. It turns out that it's infinite, but it's only half of the full story. And that was really realized in a very deep but not hard to understand paper at the time by Thomas Prosen, and that sort of started the process of explaining a lot of puzzles. The basic idea, the reason why I think this was important, it seems like something interesting happens with that Heisenberg chain model about every 40 years or so. So Bethe solved it. He was actually a graduate student. So if you're a grad student, there's something to aspire to, I suppose. He invented what's called the Bethe ansatz. The only problem was at the end of the paper, he says something like, we've solved the antiferromagnetic spin chain. We expect the generalization to higher dimensions will follow shortly. We're still waiting. These methods are very specific to 1D that he used, but very beautiful. They create a lot of mathematics. Physics-wise, a bit of progress in the 1970s was realizing that Bethe's solution, originally for the ground state, lets you also get the thermodynamics, like the free energy at any finite temperature. But dynamical properties, how things evolve in time, even in linear response, was quite confusing. I don't know if it's a problem, but I see that recorded sign up on the Zoom. I don't know if anyone can see that, but not a big deal. The conserved quantities explained some mysteries about how dynamics work and started the process in 2019. There was the follow-on that I'm kind of going to focus on. But I will sketch a little bit about how dynamics actually works in the Heisenberg chain in general. But as an example of how this is successful and how quantum computations are not that bad, the pictures here are the following numerical experiment. Take this chain of XXZ spins, or spin half particles with a simple local interaction, put the ends at 0 temperature, the ground state, and heat up the middle, and then let it go. So you expect the hot middle, the energy there will kind of spread out, and you can look at the energy density and compare the result of a microscopic classical simulation, so-called density matrix renormalization group, that's DMRG, with the predictions of a hydrodynamical theory that effectively incorporates all of the conservation laws. And just to zoom in a bit, it works better than most calculations from my group work, is I guess a way to put it. It seems like the long-time dynamics are correctly described by one simple, effectively classical equation. So I'm going to show you not all the details, but the spirit of the hydrodynamical equation that produces this, because it actually has a longer history than 2019. But first, this model here, the reason why we kind of understood this case, this is not a trivial case. It has interactions. It has a non-zero Jz and a non-zero Jxx, but it's not all the way to the Heisenberg point. We kind of knew that the Heisenberg point was somehow different and harder, but we didn't know what it was until a bold conjecture in 2019. So I'll come to that in a second, but basically, except for the Heisenberg point, like everywhere from kind of free fermions up to the Heisenberg point, that infinite number of conservation laws are effectively captured by one equation that physically makes a lot of sense, except that the formula for V here is very complicated. So if you ever took a class on old style kinetic theory, you'll have come across the Boltzmann equation, which normally has the left side is kind of the streaming evolution of a one particle distribution function. So rho is how many particles do I have at momentum k, position x, time t. The right side would be collisions. The surprise is that integral models don't really have true collisions. I'll explain what that means with a picture in a second. All that happens, the only key to the dynamics until you get to the Heisenberg point is effectively that the velocity of one particle depends on all the other particles at the same space-time point through some complicated kernel. But that kernel is all that changes between different integral models. In fact, the first appearance of this kind of equation was for a classical problem of solitons in the nonlinear Schrödinger equation. I know that there's at least one optics expert in the audience, so that's kind of this really, I think, first occurred in like classical but interesting optical equations for solitons. So where we're going is going to be the Heisenberg point, because that's where there are experiments, that's where there's a news story. And the news story is that if I look at spin correlators, they're neither ballistic nor diffusive. Instead, there's a power law 2/3. I mean, I put it on T, so that corresponds to a dynamical exponent Z equal to 3/2, which is halfway between the diffusive value Z equal to 2 and the ballistic value Z equal to 1. And the reason why this came as a bit of a surprise, we know a lot of classical problems. I'll even show you a little movie of one. We know a lot of classical problems that are described by this Z equal to 3/2, but the classical Heisenberg chain, if I just took unit vectors, is not. It's diffusive with maybe a log correction. So this is saying that the quantum chain, because it has these extra conservation laws, behaves differently, but in a famous kind of soft matter universality class. That was sort of the conjecture. All that means experimentally, it gives you something you can look for. If we had ballistic behavior, we'd have the red curve. If we had diffusive behavior, we'd have the green curve. And this KPZ behavior is in between. Particles move super diffusively, not as slow as diffusion, but not as fast as if they had a velocity. And one famous problem mathematically in this universality class, actually part of a Fields medal went for proving stuff like this, was that the leading nonlinear correction to diffusion, this here is just some kind of random noise, the leading nonlinear correction to diffusion will put you into this Cardar-Parisi-Zhang universality class. And it appears in models of mostly interfaces, but also things like traffic and so on. And we found that a very interesting conjecture. We were suspicious, we agreed with it, and we tried to figure out what are the conditions for it to happen. It happens in other chains as well, more complicated ones, but the basic story is the Heisenberg point is like a quantum critical point of the dynamics. If you have delta equal to 1, which is the Heisenberg point, you get Z equal to 3/2. If delta is greater than 1, it's Ising-like and you get diffusion. Or if you break these extra conservation laws, like in a sense, the generic case, if you wait long enough, is diffusion. And if you don't have strong delta, it's kind of adiabatically connected to the free case and it has Z equal to 1. And the pictures I showed you before were sort of interacting, but ultimately ballistic. So to give you maybe the simplest problem I know, this is called sticky Tetris. Particles drop down, they stick to each other. There's an interface that's moving linearly in time. If you were to look at the correlation functions of the width of the interface, you would realize that it's not Gaussian. It's got exponents like 1/3 and 2/3. Tetris was an old video game. This is what video games were like when I was in school. Classical computers have come a long way. Anyway, so that's an example of just a totally simple classical interface model, the interface of sticky Tetris that is in the KPZ universality class. So what's that physical picture I promised? Why the Boltzmann equation for integral models is in hindsight very simple is that what's special about solitons, if you ever, real solitons have the property that there's some lumps of energy that hit each other, they interact, but they come out retaining their identity. They come out with the same asymptotic momentum they had on the way in. So in other words, even if many solitons come together, they don't actually randomize their momentum. Their asymptotic momenta are unchanged, and that's a way to understand why there's so many conservation laws. So here, what does happen though, these dotted lines are the trajectories that the solitons of the nonlinear Schrodinger equation were on. The actual trajectories coming out have the same velocity, but they're shifted a bit. Basically, the two solitons interacted and delayed each other. And the way that connects to the Bethe equations for solving integral models is that the Bethe equations are all about phase shifts, and energy-dependent phase shift, according to Wigner, is basically just a time delay in the semi-classical approximation. So maybe it makes sense that Bethe equation quasi-particles should ultimately behave at long length and time scales a bit like that, like classical solitons. I'm going to go a little bit faster through here, but essentially we have a kind of hydrodynamics for integral models. The most subtle case was this z equal to 3/2, where we still don't understand things quite as well as we do away from the Heisenberg point, but we know that there's z equal to 3/2, and we know that some things are KPZ. In fact, the main contribution of quantum computers was showing that maybe not everything is KPZ. So first, the experimental history, and I realize there probably are not a lot of solid state experimentalists, but some people did a lot of work, so I'll sketch where it came from, and it was kind of cool how it related to history of spin chains. Potassium copper fluoride is a big three-dimensional crystal. You can pick it up. You need a lot of material to do neutron scattering, but it's a beautiful measurement of spin dynamics if you have a big crystal. Effectively, there are one-dimensional chains in the sense that the coupling along spin half chains is about 20 times stronger than the coupling perpendicular to the chains. So there's at least some energy range where the system is well described by this one-dimensional Heisenberg antiferromagnet. So what you measure in neutron scattering is the Fourier transform of exactly the spin correlator that I'm claiming will show some unusual universality class. And all you have to do is go tell the experimentalists to do something easier than what they've done in the past. And this is where I mentioned those two kinds of emergence of particles and emergence of fluids. In the past, they've measured emergence of particles. That was this kind of spin-on dispersion relation. That was famous work around 2007. So we went back to the same people basically and said, take your old crystal, heat it up. So normally you're telling experimentalists to stick things in the dilution refrigerator, which takes a long time. Here it's like heat it up to room temperature or so. And look at, instead of looking at low temperature and high frequency, look at high temperature and low frequency. And in fact, I was just at a meeting about the next generation of neutron scattering, which will be going to like even longer time scales, lower frequencies. So you're looking in a different region than where people used to look. And there's an interesting story of the crossover from low temperature to high temperature that, the part of my story that condensed matter people would find surprising is kind of answered on this slide. I'll skip over it, but please feel free to ask if what I'm saying sounds too mysterious. Anyway, there were experiments, and let's say, because I want to focus more on the quantum computing, or at least equally on the quantum computing experiments, even though I was more involved in the traditional solid state one, classical simulations are the black curve, DMRG again. Neutrons are the data points, and there's a real limitation in what you can do with the neutrons because of the crossover to 3 dimensions and scattering off the elastic continuum. So at most you can see maybe 1 decade of scaling. 1 decade is not enough to really nail down a power law, but you can say that it's much closer to z equal to 3/2, especially when you look at the full set of data, than it is to either z equal to 1 or z equal to 2. So if you like, what we could do with solids was find strong evidence that it's neither ballistic nor diffusive, and probably KPZ. And that was the story in 2021. So now, jumping ahead a year, this is the atomic experiment I mentioned. So I don't have pictures of their data. I want to explain how it's better and worse than the condensed matter data. So this is Emanuel Bloch and Johannes Zeiher's group in Munich. And they have essentially a measurement of real-time dynamics of an atomic system that emulates the Heisenberg spin chain. It's only about 50 spin equivalents along a tube. But the advantages are you can prepare special initial states that are not thermal, which would be hard in the crystal. You can control, I think the bigger difference is that you have more control over the Hamiltonian. The Hamiltonian of a crystal, you can add a magnetic field and things like that, but it's largely kind of externally provided. You don't get to tune it. So here it's a smaller but more tunable system. And they could nail down that indeed this anomalous scaling only happens when it's supposed to happen. It doesn't happen when you cross over to 2D. It doesn't happen if you get away from the Heisenberg point. So that was quite a powerful demonstration. And then maybe the new thing that motivated my talking about this particular problem, it's one of the first cases I know where for a science problem in quantum matter, something came out of gate-based quantum computers, superconducting qubits, that would have been, I don't want to say impossible, but quite time-consuming and non-trivial with the best classical simulations. And it's because this problem is special. This Heisenberg chain is a rare case where, first of all, it's one-dimensional with local interactions. That's good. But even more, it's a problem where you care about infinite temperature, because the two temperatures that are easy on a quantum computer are, in a sense, zero, because you can prepare at least some simple pure states, and infinite temperature, because you can also prepare random initial states. The roadblock I want to kind of explain is cooling. There is a good theoretical or rigorous understanding that ground states are hard. Exactly how hard the low temperature Gibbs ensemble is for different problems is kind of a big deal. If you want to use quantum computers for quantum materials or quantum chemistry, better cooling algorithms, there are some interesting ideas, but that is at the moment the big roadblock. But the great thing about this problem, I don't have the author list because someone else counted and told me they're actually 178 rather than 180. I can understand why, because there's a lot of work in this paper. It's very impressive. One thing they could measure, I will tell you, but the two cases I've seen in the last year of problems that I sort of care about being solved, or at least quantum computers contributing to their solution, have a couple things in common. What they kind of showed is that 2-point correlators, which you measure in neutron scattering, are Cardar-Parisi-Zhang-like, but at least for some initial states, and this had sort of been guessed classically by people like Prison, higher point correlators are not Cardar-Parisi-Zhang. There's something else that we don't currently understand. You could sort of make a classical analogy. So real Heisenberg chain doesn't behave like this, but a version does with logarithmic interactions. It's a bit weird. The Ishimori chain, that was the conjecture. And they said that 2-point correlators were KPZ. By higher point, I mean something like S1, S2, S3, S4 at 4 different points. And those seem to be different and not yet well understood. So I don't want to say like the original version of this paper said, well beyond what anyone could hope to do or understand with a classical computer. You know how it is. I don't think I would go quite that far, but it's impressive to me. And another example that's similarly impressive to me, and also for this other example, I know more about the exact resources because it was IBM rather than Google. There's a neat archive preprint on it's kind of a toy model related to hadron dynamics, but it's really just another one-dimensional local model, so-called Schringer model. And there, to give you a sense of numbers, 112 qubits, depth of 370, total number of gates is that. That's about where superconducting qubit quantum computers are. And at the bottom, the message I want to give is that this hadron problem or Schringer model is a lot like the spin problem. It's a one-dimensional problem with local interactions that can be addressed by time evolution of some vacuum state that you can efficiently prepare. Actually, a lot of the thought that went into it was setting that up. Most quantum matter problems are not, at least as far as we know, are not like that. I mean, they're not 1D, but even a more general problem, they're not simple time evolution of a simple state. They're simple time evolution maybe of a low temperature Gibbs state, and that's kind of the roadblock. And just why we know that's, ultimately getting to zero temperature in the ground state is a roadblock, and it's even a harder roadblock once you get beyond the Ising model. It's kind of satisfying that If you took random versions of the models that we like to study when we think about local interactions of simple qubits, say, when you go from Ising to transverse field Ising, which is adding perpendicular magnetic field, to the Heisenberg model, finding the ground states of those would be more and more powerful computers. So there's a nice, physicists and quantum computer scientists clearly think about these things with different language and so on, but at least there's some mapping of hardness in the translation invariant problems we care about to hardness in the random coupling problems. And I think that's ultimately why Google and IBM are studying these special translation invariant cases. So I think I've got just a couple minutes. Let's. Yes, a couple. Yeah. So basically, higher dimensions are intellectual frontier. I'm not going to talk. This is painful to me, but I'm not going to talk about the work my group does on finding spin liquids and so on. I think I'll show you an experiment, one material and one experiment to wrap up and illustrate, what is the 99% of quantum matter problems. Now that I've told you about the 1% where maybe current NISQI quantum computers can sort of help a bit. Ytterbium selenide is like a triangular lattice. If you want, it's like a triangular lattice interacting spin model, but not just the Heisenberg term. It has additional terms involving multiple spins, and that's what makes it hard. But there's a belief based on both experiment and theory that as you move in this ytterbium selenide family, you destroy the conventional order that would exist. The 120-degree order means like 3 sublattice spin order. As you change the chemistry, you destroy the order that did exist, and you get something new. Exactly what the new thing is that's where there are experiments that we don't yet have an approach to understand very well theoretically. So a lot of studies of this particular family of compounds, a lot of hopefully healthy competition and so on. I'll just show you how both neutron scattering and classical computation can get down to maybe below a Kelvin. But magnetic susceptibility, which is very indirect, says that something interesting is happening at 50 millikelvin. So if you like, this is millikelvin, this is the magnetic susceptibility of a crystal of this mystery material. We thought we understood it as a Dirac spin liquid, which would kind of explain this smooth behavior. And then boom, below about 25, 24 millikelvin, there seems to be some other phase with the gap. So that, what exactly that phase is, we all have favorites. But the main point, I guess, is that in quantum matter problems, sometimes you have a toy model where the physics happens on the scale of the largest coupling in the problem, like J in a spin model, U in a Hubbard model. More likely in the real world of materials and atoms, often the interesting physics happens at an energy scale, which is like, take the natural energy scale, the naive size of the terms in the Hamiltonian, and divide it by 50 or 100. And that's been the big problem with, say, ultra cold atomic simulation of high temperature superconductivity. We can't get fermions in a lattice to 50 times below the U scale. I mean, just to give you an example of why I say that, the natural scale, in a sense, for a solid, a Mott insulator like the cuprate superconductor parent materials is 10,000 Kelvin. And they superconduct, even though it's high temperature, they superconduct at 100 Kelvin. So that's 1%. That suggests that your time has to be at least 100 of the naive time that you can evolve over, and so on. So that's why cooling is so important. It seems like unless you can really, make a toy model Hamiltonian that is very far from any material, most of the time you have to get cold. And just to indicate, there is a lot of interesting emergent phases out there that we believe should exist in nature but have never been found. And if you can get cooler in a controlled way with the next generation of computers, you can find non-abelian anyons, you can find chiral spin liquids. There's a whole universe of stuff, the stuff that kind of motivated most of my career, but that I don't have time to talk about, but I hope that will serve as some motivation. So to wrap up, maybe I'll just take questions rather than reading all of this, but I wanted to end with kind of the positive message is that I really think that these superconducting qubit quantum computers are actually contributing to our understanding of a real materials problem that we cared about anyway, but it's a bit of a special problem with a distinguished history though. But there is a roadblock. There's a reason why I agree with the sense of the second talk yesterday that, for last talk yesterday, the quantum materials and quantum chemistry problems we care about are not yet easily within the ballpark of NISQ. Let me stop there.
We have several questions.